Okay, recording is on. Here we are, Math4707, October 7th. We are in the midst of discussing chapter 4, which is a short chapter on Fibonacci numbers that illustrates a whole bunch of points about numbers and combinatorics that are defined by recurrences, things that are easy to prove by induction about them. So we're going to see a bunch of those. We're going to use them as an excuse to introduce the notion of generating functions as a technique for analyzing sequences. So that's kind of where we're headed today. And then we'll see where we end up today. We might actually end up heading on to graph theory by the end. Who knows, in the second half. I put a little note on our first page here that I had been talking about a resource on generating functions that is by Greg Musiker. I realized that when I copied my old syllabus into my new syllabus for this semester, I'd somehow omitted Greg Musiker's introduction to generating functions, but now it's there, linked to the syllabus. You look at the various extra resource sheets. And I was referring to something by Sam Hopkins. He has a bunch of exercises on generating functions, which you might want to take a look at. So Musiker's intro does talk about the Fibonacci numbers as an example of use of generating functions. So if what I'm saying doesn't make sense, you might want to read what he says, compare it to what I said, just read him instead. In the end, hopefully it'll make some sense. So any questions before we get back into the Fibonacci numbers? All right, so let me remind you, we were discussing those. Fibonacci numbers Fn were our first sequence of counting numbers that were defined by a recurrence. So Fn plus 1 is supposed to be Fn plus Fn minus 1, and this is for n greater than or equal to 1. And they're defined as numbers starting with F0 is 0, F1 is 1, and then we started tabulating some more of them, you know, and we got, oh gosh, let's just have our table out here again. And Fn, a little bit of the table. We're not going to do that much. Maybe go through the first, I don't know. Let's see, 0, 1, 1, 2, 3, 5, 8, 13, 21. Maybe I'll do 2 more just to get to 9 and 10. What was this? 34 and then 55. Okay. And so these were the initial conditions that define them. This is the recurrence that defines the rest of them based on the initial conditions. And we started noticing some things like, what did we notice? That F3m is even, whereas we noticed that F3m plus 1 and F3m plus 2 were odd, so they went even, odd, odd, even, odd, odd. In other words, 2 divides F3m, and 2 is the same as F3. So we notice that, whoops, F3, which is 2, always divided F3m. We notice that multiples of 5 in the subscript, F5m, were divisible by 5. All right, that was our example of like F0 is 0, that's divisible by 5. F5 is 5, divisible by 5. F10 was 55, also divisible by 5. And we saw a few more, and we proved it. 5 divides F5m. And the point was that we then later noticed, oh, and 5 is F5. And then we guessed, based on this, that, F3 always divides F3m, F5 always divides F5m. We guessed, and maybe we even looked at F7 at a couple examples, that Fk divides Fkm for all m greater than or equal to 1, and k positive. And so we were in the midst of proving that. Sorry, let me going a little too fast there. Any any questions on what I just wrote on this review on the front page? So we were proving that, right? Theorem, Fk divides Fkm for k and m greater than or equal to 1. And what we actually decided was we were going to prove proof. We deduce it from a lemma that we'll prove instead. That said f of a plus b plus 1 satisfies some kind of a recurrence that is going to turn out to generalize the original Fibonacci recurrence. It went like this: fa plus 1, fb plus 1, plus fa fb. Let me make sure I did not copy that wrong. Yep, that is it. And that's for a and b greater than or equal to 0. And the way we deduced it from that lemma, right? I haven't yet proven the lemma, but assuming we could prove it, what did we do? We just made some artful choice of the a and the b. What did we do? We picked, let me just remind myself what the choices were. A is going to be k times m minus 1. B is going to be k minus 1. And then the lemma says, look at this, f of a plus b plus 1. Okay, so that's going to be f of k times m minus 1 plus k minus 1 plus 1. And you see what all that is, and you realize, okay, that's k times m plus, wait, is that what I wanted? Sorry, let me make sure that's what I wanted. K, I want it to be km. Did I get km? Km minus k plus k. Yes, I did get km. Good. Check me on that. That these three things all add up to just k times m. There's a lot of cancellation there. Good. And the lemma would say that this is equal to, all right, we got f of a plus 1, f of b plus 1, plus f of a, f of b. And then that's going to be, all right, f of a plus 1 is k times m minus 1 plus 1. Not so thrilling, but f of b plus 1 is fk. That's good. It's divisible by fk. And then we got the f sub a is f k times m minus 1, whereas fb is fk minus 1. And then the point here is that makes it divisible by fk because it's got a factor of fk in it. And this one is divisible by fk using induction on m. So the point was we were able to do an inductive proof on m. We checked the base case last time of m equals 0 or m equals 1. It was not very hard to check that this was true when m equals 1, for example. And so what we would get then is that fkm is equal to this expression in which both of the two terms are divisible by fk. All right? So it only remains to prove the lemma. That's kind of where we were last time. But any questions about why we're reduced to proving the lemma? Let me emphasize that lemma, maybe put it in blue, maybe copy it so that we can take it to the next page. Any questions before we start proving the lemma? Okay. And before we do it, let's just check a couple of instances to see that it's saying something reasonable. Let's check the instances where A is 0 and A is 1 and A is 2, just to see what it's saying. Does it seem plausible? But I mean for all B. So I'm just going to fix the A for the moment and see what this lemma is saying in those cases for an arbitrary value of B. Well, for A equals 0, what does this say? On the left side, I've got FB plus 1. On the right side, I've got what, an FA plus 1. Okay, A is 0, so that's F1. And I got an FB plus 1. And then A is 0, so this is F0 times FB. What does that say? It says, okay, F1 was 1. And F0 is 0. So it's just saying FB plus 1 is FB plus 1. It says nothing. Or nothing interesting. FB plus 1 is FB plus 1. Fine. What about the A equals 1 case? Hopefully that's a little more interesting. In that case, it's saying FB plus 2, right? Because A is 1, so A plus B plus 1 is B plus 2. And on the right, we're going to have an F2 here and an F1 there. So let me put those in. F2, FB plus 1 plus F1, FB. And it turns out both of these are 1s, right? Remember, F0 was 0, F1 was 1, and F2 was the sum of the two, is 1 plus 0 is 1. So this is actually FB plus 1 plus FB, and that statement is just the original recurrence, you know, with the subscripts shifted slightly. Okay, so that's reasonable enough. This thing really is generalizing our original recurrence when we take the case A equals 1. What about the case A equals 2? Well, I mean, let's just see to get a feel for it. It's going to be giving us some kind of new recurrence. It's going to say FB plus 3, right? Because now we're adding A plus 1 to B, and A is 2. Is FA plus 1 is going to be a 3 in front of FB plus 1, and FA is going to be F2 is a 1 times FB. Okay, so what did we say? F3 is a 3. F2 is a 1. So this says FB plus 3, and it's writing it in terms, not in terms of the previous value, which would be FB plus 2, but it goes back to 2 values that are not sort of next to previous and then next to previous, but with some coefficient in there. And this should remind you a little bit of what was going on when we started doing the proof that 5 divides F5M. There's a raised hand.
Yeah, should it be 2?
Oh, probably should. Yep. Thank you.
Do you get a notification for that, or how does that even work? The raised hand.
Sorry, say it again, William. I've got my volume really low. Say that again.
Oh. Do you get a notification if I raise my hand, or is it just like you see it on the participant list?
I think I got it because the chat window was closed. Something showed up that it was a raised hand. Yeah, and Rory and Emma, thanks also for checking me. Yeah, I do make tons of mistakes, so please do, indicate somehow. I think if you just write something in the chat window, if I don't have it open, I see a little notification that something came up in the chat. So I think either way works. Good. And do we believe this thing? Yeah, I think we do, because let's just check this. This seems new, but it can be proven in the same way like when we were doing that proof that 5 divides F5M. This guy by the recurrence is FB plus 2 plus FB plus 1. And now we can try to get rid of the FB plus 2 is FB plus 1 plus FB. And yeah, that's exactly what we wanted. Okay, so it's new, but it's not too surprising. Okay. All right, so finally, let's prove the lemma, the thing that would prove our original theorem if there are no questions. And in doing so, for the proof of the lemma, I wanted to illustrate the idea that for each value of A, we're getting some kind of a lemma, right? And so what we can try to do is actually prove it by induction on A. For each value of A, there's an assertion. We checked that assertion was correct for A equals 0 and A equals 1 and A equals 2 already. So we could think of them as base cases for an induction on A. Let's use induction on A. So fix A and prove the assertion for all B. This may be a slightly different structuring for an induction than you've seen, but when you have a statement that has two parameters in it, there's both an A and a B in the statement, you can actually try tricks like this, where you fix one of the parameter, use it as something to induct on, proving the assertion for all values of the other parameter. Okay, so let's just to make sure we understand, base case, A equals 0, we checked, right? That was this assertion right up here. For all B, it says FB plus 1 is FP plus 1. Done. Okay. And if we want, we could say, all right, we also checked, beyond the base case by 1 and beyond the base case by 2. But let's just jump now to the inductive step. So what are we assuming? Let's be clear. We're assuming we've proven this recurrence FA plus B plus 1 is FA plus 1, FB plus 1 plus FA, FB for all smaller values of A and all values of B. Okay, so for each fixed smaller value of A and all values of B, it's been proven. Pretty good? And now we'll prove it, and now prove it. Assuming that, so what am I gonna do? I'm gonna say FA plus B plus 1. And I'm gonna do something that seems like I'm cheating, but it's not. I'm gonna say, oh, that's F A minus 1 plus B plus 1 plus 1. Right, and the idea is that is smaller. And even though the B got bigger, I don't care, because for the smaller values of A, I dealt with any value of B, no matter how large, already. Okay, so let me emphasize. Didn't mean to put values. Okay. And why am I emphasizing this? Because now we're using our inductive hypothesis to write this. As f of, okay, this thing plus 1, which is FA, this thing plus 1, which is B plus 2, plus f of this thing and f of this other one. Everybody see that? I just used the inductive hypothesis, but with A being one smaller. Okay. And now we just have to see whether this helps us, right? The thing that I have on the right-hand side doesn't look right. I'm trying to get to this. I've got this. So maybe what I should try to do is take this thing with the b plus 2. That looks like I should try to make its subscript smaller. Okay, let's try that. We know that's b plus 1 plus f, sorry, fb plus 1 plus fb. Using the original recurrence to trade this for this. Maybe I'll do I think I was using some colors like this before to say I'm doing the original recurrence. And now this actually looks a lot better because I see an FAFB, right? There's an FAFB, that's something I wanted. The other thing that I want to get is this. And I do see a couple of terms with FB plus 1 in them. And they got some coefficients, and maybe those coefficients combine correctly to give me that, and they do. So, looking good. Bad color, good color. So what do we get? We get FA plus FA minus 1 times FB plus 1, combining coefficients. And I'm left with an FAFB. And using the recurrence backwards, this is FA plus 1, FB plus 1 plus, sorry, plus FAFB. Everybody see what happened there? Questions? Anybody queasy about the way we did the structure of the induction?
Slightly.
Yeah, so come back and think about this. You might want to think about the pairs A and B, like plotting them in the first quadrant in the, in the plane. For which values of A and B did we prove it first? And then, which
I don't think that's the problem I have. I think it's more just like how we're notating it. Because, I feel like there are kind of two, when we're saying A and B, there's, like if you look at the line you have, F sub A plus B plus 1 equals F sub, like all that stuff.
This one?
That line, yep.
Yep.
You're, like, it seems a little bit kind of messy to use A both for, here, I'll talk about it after lecture. It'll just be better.
Yeah. But I do want to emphasize, sometimes these things, they do seem a little shaky the first time you see them used, and it takes a little while to ponder, like, oh yeah, was that actually reasonable? Was that kosher? Can you really do that? It's good to think it through.
Yeah, I totally understand how, like, this is factually correct, how the proof works, except I just don't like how it's notated or how it's presented.
Well, maybe it can be improved. Good. Other questions before we keep going with more Fibonacci's and generating functions? Okay, so one of the things that people noticed about Fibonacci numbers was their growth. So let's ask a question, not in that color. Question: how quickly do the FN grow? Maybe let me put in a little dividing line here. As n goes to infinity. Right, is it linear? Are they growing, kind of like an arithmetic sequence? Actually, let's just, so Sorry, there's
If you think about it, their rate of change has to do with their value, so it should be exponential.
Yeah. And Theo says it has something to do with the golden ratio. That's going to be where we're headed. And so let's talk a little bit about this. If you look back, let's just look at a little bit at our data. And you start to look at it and you begin to realize, no, it's definitely faster than linear, this growth. And because you keep adding this previous one and they're getting bigger and bigger, it's certainly not linear. You might think it's like quadratic, like something like n squared or a constant times n squared. But pretty quickly, quadratic. Maybe it's geometric. Maybe there's like some constant multiple, geometric, like, r squared, or maybe I shouldn't write r, but some initial term, like an initial term, ar squared, ar cubed, something like that. And that actually, people started to realize, seemed to be close to the truth. If you begin to experiment, you look at these things and like, what are some of these first few ratios between the terms? Right? Geometric means you would have fn plus 1 over fn being like some constant ratio. Well, if you start writing them down, like 2 over 1 and 3 over 2 and 5 over 3 and 8 over 5 and so on. What are some more of them? 13 over 8, 21 over 13. People noticed that those things looked like they were converging. Okay, and so they got the idea that there might be some kind of a formula that looks geometric. And let me just see what we had in the chat. dfdn is k times fn. Yeah, something like that. And this business about the golden ratio that Theo mentioned. Yeah, so people eventually figured out a precise statement. And so let's just, where's my precise statement? Okay, yeah. So let's move on to section 4.3, which is an exact formula for the Fibonacci number. And this is maybe a little bit surprising that you can come up with an exact formula. Let me emphasize that by putting a question, a little exclamation. Can't write in red. Okay, so the book's derivation of this exact formula is okay. It's just slightly unsatisfying as to how they would have guessed it. They don't really explain how you might have guessed this exact formula that they come up with. And so what I'm going to do is just use this as an excuse to talk about generating functions, which definitely would have predicted this, and we'll prove it. So we'll get this formula by considering this generating function which is a power series. Considering a power series. Okay, and I mean this like in calculus, like when we had power series for sines and cosines and logs and all sorts of things like this, that basically just has the Fibonacci numbers in front of powers of x. So you put fn in front of x to the n and sum them up. So you're thinking of that x as just being a variable. All right, so I could write it like this, n greater than or equal to 0. No, maybe I'll write n equals 0 to infinity just to use a more traditional kind of notation. Fn x to the n. And so what do I mean? I really mean in front of x 0, so it's going to be 0 times x to the 0 plus 1 times x to the first plus 1 times x squared plus 2 times x cubed plus 3 times x to the fourth plus 5 times x to the fifth plus 8 times x to the sixth, and so on. It goes on infinitely like that as a power series. Maybe let me make that so they can all fit on one line here. Okay. And this is called the generating function for the Fibonacci numbers. And in general, when you have a sequence of combinatorial numbers and you make them the coefficients in front of a power series, you call it the generating function for that sequence. Let me notate the sequence as Fn as n goes, from 0 to infinity. And you've actually already seen some generating functions in your life. In fact, even in this class, we've already seen a generating function. Let me do one not from this class so much, but well, the counting function was from this class. 2 to the n. So let me take the sequence an is 2 to the n. This is counting, right, the number of subsets of the numbers 1 through n. Right? And this thing has a generating function that is not too hard for us to write down and actually simplify algebraically. Okay, so let me call its generating function, just because I called my sequence a sub n, let me call it a of x rather than little f of x that we were using for the Fibonacci's. So what is this going to be? I put 2 to the 0 times x to the 0, 2 to the first times x to the first, plus 2 squared times x squared, plus 2 cubed times x cubed, and so on. Right, so what is this? This is 1 plus 2x plus 4x squared plus 8x cubed, and so on. And so let's think about this for a moment. Nobody, don't write anything in the chat. No, nobody pipe up yet, and please keep muted. But my claim is that this infinite expression, right, that I have to write with a dot, 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 actually has a nice, simple, finite closed form that you know of. Anybody know how to write that as a closed form? Yeah. Okay. Anybody who wants to can put it in the chat now. This one I claim actually will fit in the chat. It's that small. Yeah, I don't think that's right. William wrote 2 to the x plus 1 minus 1. I don't think so. Anybody know how to evaluate a series that looks like this? You got to think back to your calculus skills a little bit. Perhaps that's misleading. It's not that it needs any differentiation or integration. It's just like something you probably learned back when you were doing power series and calculus. So first of all, this is a geometric series, right? This term, going from this term to this term, you multiplied by 2x. Here to here, you multiplied by 2x. There to the next one, you'd be multiplying by 2x. So it's a geometric series whose constant ratio between the terms is 2x, right? Anybody remember how a geometric series goes when you have like a plus ar plus ar squared plus ar cubed and so on? Anybody remember how to sum that? Yeah, I think that's correct. William, you wrote, I didn't have an a naught, but I think it's like that. Mm-hmm. And so in this case, right, our first term, our a naught, or the term right there, that a is a 1. So on top, we're going to have 1 over 1 minus, and then we said the ratio is 2x. Everybody agree? Okay. So that's not bad. That's an example of a generating function that looks pretty good. Let me show you another one. Why is this thing not straightening? That's supposed to straighten when I do a line like that and hold it. There we go. Let's do another example. What if I take the binomial coefficients as you go along a row for Pascal's triangle? In other words, fix the n, which tells us which row of Pascal's triangle we're in, like n equals 1, 2, 3, 4, 5, you know. Did I do that right? Getting messy. No, I didn't do that right. There's a 10 here, a 5 and a 1, and so on. And consider the sequence, yeah, let me call them BK. So it's going to be n choose k. In other words, n choose 0, n choose 1, n choose 2. And now this is actually a finite sequence. It stops because it's a row of Pascal's triangle, so it's finite. Then this thing, this b of x, right, is going to be b0, you know, times x to the 0. Okay, so it's going to be n choose 0 times x to the 0 plus n choose 1 times x to the first plus n choose 2 x squared, and so on, stopping with n choose n x to the n. And this thing also has a pretty simple algebraic expression, which we've seen actually in this class. Right. That's right, and there it is. Right. This is just our version of the binomial theorem in which we took the y to be equal to 1. Okay? And I want to remind you that we actually use this. The fact that this summation had this expression, right? If you remember, we took x equal to 1, and we got 2 to the n as the sum of n choose k. We took x equals -1, and we got 0 was the sum of the binomial coefficients with plus and minus signs. And we also, we took a derivative and then set x equals 1. And we got, what did we get? Let me remind myself. We got n times 2 to the n minus 1 is the sum of k times n choose k. You know, anyway, you can go back to some previous page, and we really actually did use this generating function to deduce a bunch of identities before. So that was really me sneaking in a little bit of generating functions ahead of time. Okay. Question? All right, so for the Fibonacci generating function, here's what we're going to prove and how it's going to get us an exact formula. Fibonacci numbers Fn have this thing, this Fibonacci generating function. All right, so let me just remind you, this is this thing that goes 0, well, 0 times x to the 0, 1 times x to the 1, and so on. It's also got a very simple algebraic expression. In the denominator, it's this, and in the numerator, it's that. It's that function of x. All right. So that's the first thing we're going to show. That's A. B, and from this, we will deduce that Fn actually has this exact formula. It is, let me remind myself just to make sure I don't get the, oh yes, it's always the factor in front that I have trouble remembering. 1 over the square root of 5 times phi of n minus beta of n. I'm going to tell you who this phi and beta are. They're two real numbers. One of them is the golden ratio that someone was talking about. This is 1 plus square root of 5 divided by 2. It's approximately 1.618. It's called the golden ratio. It's greater than 1 is the important thing. And that's the one that's going to control the growth of the Fibonacci numbers. The other one, this minus beta to the n, is going to be smaller. It's going to actually be a negative number. It's 1 minus the square root of 5 divided by 2. And so it's about negative 0.618. And the point is, in absolute value, it's less than 1. So I need space. So let's take this theorem. Okay. Should really have some kind of dividing line. Let's take this over here to the next page. To the third assertion, and hence, in the limit as n goes to infinity, what happens is the phi to the n just completely dominates, because phi is a positive number, it's bigger than 1. You keep multiplying by it, you're getting bigger and bigger. Geometrically, you're growing, like with approximately this ratio. This term, which you're subtracting, and it's either getting added or subtracted because it's a negative number, so you're raising it to various powers, it's changing sign, but because it's less than 1, it's just getting tinier and tinier. So it already starts out, like when it's beta to the first, it's already something less than 1 that you're adding. Then in the next term, it's something much less than 1 that you're subtracting, right? This thing becomes negligible. Yeah, I guess I should just say it's that. It's about 1 over square root of 5 times the golden ratio to the n. In fact, maybe what I really want to say, that's not really a limit. That's not a limit. Let's not phrase it like that. All right, I'm gonna make an imprecise statement and then a precise statement. As n goes to infinity, the Fibonacci number is approximately 1 over square root of 5 times phi to the n. And what we can say is, in the limit as n goes to infinity, the ratio between them is phi, the golden ratio. And just even be slightly more precise. Okay, I said I was going to give you an exact formula. In fact, this one, the one that was imprecise, but let me emphasize it because it's pretty darn close. What we can say precisely is that Fn equals the nearest integer. Actually, can I say whether it's less or greater? I have to be careful here. I think I can actually say it's rounding down if I want to be precise. Yeah. Fn is equal to rounding down 1 over square root of 5 times phi to the n. So that's the floor function again, the integer that's less than or equal to it and is the closest one. Yeah. Yes. Question. E equals pi equals 2 phi, ceiling floor function, what? Totally confused. You'll explain that one to me during the office hour, will you? Oh, the thing that I was almost drawing, yeah. And how did we get from A line 1 to A line 2? Sorry, in other words, how did I get to this? Is that the question, Theo? Right, we haven't gotten there yet. And a better question is even how do I get from this to this? I'm going to use this to derive this, and I haven't shown you yet how we're going to derive this. So we're headed there. To be proven. Are we good with where we're headed? All right, so let me first of all say what's with the golden ratio? Oh gosh, before we do that, how's about we take some break, right? I went about 5 minutes over here. Okay, so we are, yeah, maybe even 6 minutes over. So I'm going to turn the recording off unless there's a quick question that people want on the recording. Any
I have one
question?
quick question.
Yeah.
For like the floor thing that you wrote, is that true for like what ends is that true for? Because I feel like you must have to
No,
limit it to some
I
degree.
think actually this is true for all n.
Okay.
I believe so, but we'll try to check me carefully later. Okay.
Should, just to be safe, should we say all n over or greater than or equal to 0? Because can you
Yeah.
extend the Fibonacci backwards?
Yeah, we're not even extending them backwards now. We're just only saying for n greater than or equal to 0. Good. Other questions before I turn off the recording so we can take our break?